In this clip, we're going to start looking at the graphs of the reciprocal trig functions. We looked at the definitions of the functions in the last clip, so this time we're going to see what happens if we try and graph them. Okay, so we have on the autograph screen the curve y equals sine x. I've got my x-axis in radians, and let's have a think. Now, if we're going to plot the reciprocal of this function at any point, so the easiest points to think about, I suppose, are when the value of sine x equals 1, because the reciprocal of 1 is 1. So we know that the graph of the reciprocal here, which is going to be cosec x, is going to meet the graph of sine x at the point where sine x equals 1. But as sine x increases, cosec x is going to have to decrease in order for their product to remain constant at 1. Similarly, as sine x is positive, cosec is also going to have to be positive in order for their product to be positive 1. And when sine of x is negative, cosec is also going to have to be negative in order for their product to be a positive number. Now, if we think about where sine of x has roots, where sine of x equals 0, the value of cosec x is going to be 1 over 0, which is going to be undefined. That means that the graph of cosec x is going to be undefined at the point where sine x has roots. Okay, let me plot cosec x on top here. So we have cosec x, and there is your graph for cosec x. So you should be able to see, if we start from x equals 0, the sine of x goes up, the cosec comes down until they meet at sine of x and cosec of x both equal 1 at that point. Where sine has a root, cosec has an asymptote, a vertical asymptote. And if I now take away the graph of sine of x, something that you may not have noticed there may become more apparent. Now, the cosec x graph, yes, it does repeat in the same way that sine does, but it does not have any values of cosec x between -1 and 1, or with a modulus less than 1. Okay, if we now go to the notes that you're going to need from this. So if we go back up to the top, these are my graphs of reciprocal trig functions. They're a bit tricky to draw, so I've cheated and stolen them from autograph. So this is the graph y equals cosec x. It is the reciprocal of y equals sine x. So as sine x goes up, cosec x comes down. So the olive-coloured one is cosec, and the red one is sine of x. So if we have a think about the range of cosec x, so if y equals cosec x, then y has to be greater than or equal to 1. The cosec does not. There's a sort of no man's land between y equals 1 and y equals -1, into which it does not go. So the modulus of y is greater than or equal to 1, or you could say that y is less than or equal to -1, greater than or equal to 1. I prefer the modulus notation, seems to make more sense. And if we think about the domain of cosec x, well, we have asymptotes at everywhere that sine of x had zeros, had roots, which is at 0 plus n pi. So they're appearing every pi radians. Okay, and the other way of writing that is that x can be any real number except that. So I'm now defining the domain, which is in effect going to define these asymptotes for me, that x cannot equal any straight multiple of pi. Okay, hopefully if that makes sense, then as we move on to the next graph, this should make perfect sense. So y equals cos x. Now, y equals cos x is just a shift of y equals sine x. So all the things I said before about sine and cosec are going to apply here for cos x and sec x. So we have the same graph as we had before. It is shifted, but again, as cosec goes up, sec comes down. As cosec is positive, sec is positive. As cosec has roots, sec has asymptotes. Okay, but the whole graph is just shifted version of the cosec graph. So, hello. So we're trying to draw here y equals sec x, and the red is y equals cos of x. So I have that the range of y equals sec x is that y is greater than or equal to 1, or y is less than or equal to -1. It can be equal to 1 or -1, remember. So another way of writing that is that the modulus of sec x is greater than or equal to 1. Okay, and if I have a think about the domain, or any values of x for which this is not defined, it's not defined at any point where cosine had a 0, had a root. So my x can be any real number except, so x does not equal pi over 2 plus n pi. Okay, so they're my domain and my range of sec and cosec. Now, the real reason that I've done this on autograph is because the tan and cot one's really awkward to draw. So here's tan. Now, tan intrinsically has roots of its own and asymptotes of its own. So if we think about when tan has roots, when tan has zeros, the reciprocal cot is going to have a vertical asymptote. But also when tan has an asymptote, then the reciprocal cot is going to have a 0. So the restriction on the range of cosec and sec does not apply here. So let me add y equals cot x. There we go. Now you can see that this one is a bit awkward to draw. So when tan has a root at x equals 0, we have a vertical asymptote in tan. Again, both are going to be positive for the same values and both are going to be negative for the same values. But we have this new thing that the range of cot is not restricted, because cot has solutions and it has values from negative infinity to positive infinity. Okay, so my pre-copied graph here. So the red graph is tan x, and again the olive graph is cot x. So y equals cot x. We have solutions to cot x equals 0 at the places where tan of x had an asymptote, so at pi over 2 and every semi-rotation, so every n pi thereafter. And we have that the range of y equals cot x is that y can be any real number. Okay, and the domain of y equals cot x, we have that x can be any real number except that x cannot be any multiple of pi.